Good afternoon, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Networked Intelligence at the Robert Bohr Center for Cyber Physical Systems, IISc. Today's talk is by Dr. Abhishek K. Gupta, and he will be speaking on fundamentals of vehicular communication networks with vehicle platoons. Dr. Abhishek K. Gupta received his BTech MTech dual degree in electrical engineering from IIT Kanpur in 2010 and PhD degree in the Department of Electrical and Computer Engineering at the University of Texas at Austin in 2016. He is currently working as an assistant professor in the Department of Electrical Engineering at the Indian Institute of Technology, Kanpur. He was a recipient of the Young Faculty Fellowship 2022 by IIT Kanpur and GEFS Leadership Award in 2009 by General Electric Foundation and Institute of International Education. He is the author of the books An Introduction to Stochastic Geometry, Numerical Methods Using MATLAB, and MATLAB by Examples. Previously, he was working as Senior Standards Engineer at Samsung Research America in Dallas, Texas. In the past, he has worked with Applied Microelectronic Circuit Corporation, Futureway Technologies, and Nokia Networks. Before we move on to the talk, we would like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I will be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk. And for questions, you may ask Dr. Gupta directly. Over to you, Dr. Gupta.
Hi, thanks. Give me a minute. Actually, some technical problem is occurring. Just give me a minute.
Sure, sir.
Okay, is my screen visible?
Yes, sir.
Okay.
Sir, I think you are on mute.
Yeah, hello everyone. Thank you for coming to this talk. So today I'm going to talk about one of my work on vehicular communication with platoons. And if you have any question, you can ask a question in between also. I will be happy to answer any question in between. So let me start. Can you hear me properly? And you can see my screen, right?
Yes, I can hear you.
Okay. So at any point, if I get disconnected, just let me know because sometimes the network is not very good currently here. Okay. So hello. So I'm going to talk about this work, fundamentals of vehicle communication with vehicle platoons. And this work was done by two of my students, Kaushleen and Raju. This was also collaborated with Professor Dhillon. So this is currently in submission phase. You can look at the paper also. So let me talk about. Let me start with vehicular communication. Vehicular communication in general means where you're trying to communicate either between the vehicles or from a base station to a vehicle. And what can be the applications for that? For example, when you're driving, suppose you may need some critical information about which roads may be congested, which is the best traffic route. And such kind of information, which are actually critical, can be given to you in real time using vehicular communication with the help of some base stations. It can such kind of information can also improve road safety and can better manage the overall traffic. Along with that, it can also provide you some accessory services. For example, you can update the software of your car, or you can get some entertainment services in real time. And also, this can be used when you talk about autonomous vehicles. This is also essential. This vehicular communication can be very helpful to get the full potential of such kind of services. And when we talk about this vehicular communication, we have in mind this V2V communication, which is vehicle to vehicle. You can also talk to infrastructure, which is like a cellular infrastructure. Uh, so you may have many base stations, either along the road or maybe like regular base station, and you can have communication from those. So that we term as vehicle to infrastructure. And then we can also talk about vehicle to everything, like you can have other devices also which we can communicate to. One thing we would like to say that when we think of vehicle communication, we many times think that the vehicle itself is capable of communication. That is definitely true, but if the vehicle does not have these features, any mobile devices which is present in the vehicle can be used as an end device. So, in general, this is very much possible to have these kind of communication capabilities at vehicle nowadays. And because of their potential, industry and both academia is interested in understanding vehicle communication more. And there have been some standards also which we are talking about in vehicular communication. So today, what I want to focus for here is a particular type of a vehicular network where vehicles are moving in a platoon. So what do I basically mean here is that this vehicle can do some kind of cooperation. They move in a group, and this may be possible because they may have some shared route or the part of the route. So suppose they want to go from A to B, so it can be divided into different segments, and each segment you can club the vehicles together which are going to a single route. So what can be advantages of such kind of platooning is, first is if you can manage these platoons, then your overall traffic management become local. There you can have better traffic efficiency. You can maintain the distances between these vehicles. They're communicating with each other. So this can avoid collision. And because these vehicles are moving together, this can also reduce unnecessary stops, right? So vehicle can move in a regular speed, and this will increase regular fuel consumption and also reduce pollution. So this is a good way to optimize road capacity. Also, when you're moving in platoon, you can decrease the inter-vehicle distances. And because of that, you can achieve more roads, more vehicles in a unit length of road. So when we talk about this vehicular platooning and vehicular communication, we see that there is a one-to-one relation between these two. First one would be that the platooning actually enables communication. How we can see that in a platooning, we can maintain some fixed distance between the vehicles, and that communication will be line of sight. So you can always assume in that in a platoon, you have at least few vehicles around you, which are in line of sight direction. So you can always communicate between them using line of sight communication. Because of a distance guarantee, you can also have a guarantee on the vehicular to vehicular communication. This V2V communication can help in collision and hazard warning and can improve overall traffic. And along with that, if one vehicle, you can treat them as a platoon head. If that is able to receive information or communication from some infrastructure, then that can act as a platoon head and can pass the information to every vehicle. right? So even if each vehicle may not be directly communicating to the base station, one vehicle can communicate. So this can help optimizing resources at the base station. So that is one side, that the platooning is actually helping communication. But we can also see that the platooning is not possible without communication, because you will be having a smaller distance between the vehicles. So you need to have very fast communication between these vehicles. And that's when way-to-way communication can help us to reduce collision when we talk about this plan. Okay, so there is a two-way connection between platooning and communication, and so that's why it's very important to understand how platooning affects the communication, or how communication affects platooning, and how we can jointly compute the performance of such networks. We are putting platooning together with the communication. Okay, so this is in contrast with independently moving vehicles. We can call them. So in this case, the vehicles are not coordinating with each other; they are moving on their own. So you can call them non-platoon vehicles or independently moving vehicles. So when you look at these vehicles moving on a road, you can see that these vehicles are really random because they are moving independently. They are making their decision independently. And if you consider that there is a cellular network which is serving these vehicles, then it may happen that some base station have large load, some base station have low load. And there is also no guarantee on the minimum distance, but maximum distance between the two vehicles. So this makes communication a little bit harder. Okay, so so now there's a lot of work which talks about how we can model and analyze these non-platoon movements of vehicles, right? So if you think like there is a road, straight road, and then there are vehicles on this road. If they are independently moving, they will be independently distributed along this road. And so each point here you can see this as a vehicle, and each of these point, I see them collectively, we can model them using Poisson point process. Okay, so the question arises: what is this point process? So I will describe a little bit about what are point processes, and this whole theory is a part of stochastic geometry. So let me first define a general point process is a set of random points. Okay, you can have a space, and you can have many points on the space, uh, which are distributed. So the total number of points can also be random, and the location can also be random. So, uh, so this point process basically describes a particular type of distribution of these points. And as I said, I would be focusing on Poisson point process. So a Poisson point process is a particular type of point process which satisfies two properties: that if you take any set A, number of points in that set A is again random, but it is distributed as a Poisson distribution with parameters lambda into size of A. And lambda is known as the density of the point process. Okay, so if you have 10 points per meter square and you take 200 meter square area, then you will have 10 into 200, 2000 points on the average in that set. Okay, sometimes it can be more or sometimes it can be large, but overall, if you want to calculate how many points are there, the distribution will be a Poisson distribution. And the second property it has is, if you take any two disjoint sets, the number of points are independent. Okay, so basically, you can talk about different areas. The point process is independent in those areas. So this independence property is a particular property of the Poisson point process. So here I've showed you a one-dimensional point process. I've taken a one-dimensional set line, and there these points are located. So if you take any, if you take any, if you take any set A of some length L, the number of points in that will be Poisson distributed with parameter lambda into L. Okay, using this formula, you can also calculate the probability that there is no point. So phi is equal to 0. If you put n equal to 0 here, this will be e to the power minus lambda A. And this gives you the void probability. Okay, the way you can characterize point process is using Laplace functional or probability geometry functional. So recall that when you talk about random variables, you can you can characterize them using Laplace transform, okay, which is expected of e to power minus si. Similarly, for point process, you can define something called Laplace functional. So suppose there is a function from some d-dimensional space. So I'm thinking of a point process on a d-dimensional space. So there is a point which computes a function on each point, and this gives you a real positive value. Then the Laplace function is defined as expected value of exponential minus summation of that function over each point of the point process. So you can see all the points on the point process. You compute the function values, take summation, do exponential minus this, and compute the expectation over different random realization. We get the Laplace function. Similarly, probability generative function will be defined as product of fxi uh, and the expectation. So both are related. Basically, if you know PGFL, you can compute Laplace function and vice versa. And once you know Laplace function, they will characterize the point process completely. So I'll just show you for Poisson point process with density lambda, the Laplace functional and the probability functional is given by this simple equations. You take for PGFL, you take the function, do 1 minus and integrate it, and the exponential of that will give you the PGFL. Okay. So what is the use of this PGFL or Laplace function? Suppose you want to compute a distribution of number of points in set B. Then you can take this function, indicator x belongs to B. And if you take the summation of overall points, basically you will see this will give you the number of points in a set B. Now, if you go back here and compute this expectation, you basically get the Laplace transform of the number of points in the set B. Okay, so if I just put this back here, this will be summation of fxi, which is total number of points in B, and this will be the Laplace transform of that. Similarly, you can use this PGFL to compute the interference, because that can also be written as summation over all base stations. Similarly, you can compute basically any random variable associated with the point process using the PGFL and Laplace function. Okay, so let me come back to our vehicular deployment. If you have these vehicles, right, you can take any set R and you can talk about how many points are there in this set R. You can compute the Laplace transform or the probability generating function of these points using the Laplace function. Okay, so why we are interested in this PGF? See, this is the total number of points in any set here is basically an integer valued random variable. Okay, positive integer random variable. So we can compute the PGF of it, and if you know the PGF, you can basically compute the PMF or the expectation and variance very easily by computing the derivative of this PGF. Okay, so in this work, we have mainly focused on computing the PGF so that we can compute this probability functionals and the the probability mass function and the moments very easily from this. Okay. So now the way we can model is the vehicles on the straight road can be seen as a point distributed over the line. Vehicles can be modeled using a one-dimensional Poisson point process for independently movement. So I denote psi as equal to pi, where pi is a point in the real line, and you have different numbers. So you have p0, p1, p2 like that. And these all points in a point in the real line, and together they construct a random set, which is the one-dimensional point process. And I'm assuming a uniform deployment of vehicles. So you have constant density per unit. So inspired from this, we will think about how we can model the platooned movement, right? So if you think about platoon movement, you have basically different platoons, and each platoon you have some vehicles, which are right, and these platoons are independent of each other. right? Now, because of the independence, platoons itself are distributed randomly. So, if it let us look at how this modeling problem is and what are the complications here. In the overall network, we have three layers of randomness. First is we are talking about Platoon vehicles on roads. The roads itself, the road layout itself is irregular. You may have multiple roads which may be intersecting, they may have different orientation. So first set of randomness is how do we model this road layout? Second is suppose you know the set of roads, then you need to know where the platoons are located. And then you have to find out the vehicles in each platoon. So there is a three-layer of randomness, and to model this, we require some kind of point process which have three level of randomness, right? Which we call triply-stochastic point processes. So the question we want to ask is, how do we model this? What will be the mathematical properties of this new point process? And once we have this traffic network, how do we incorporate the vehicular communication network over that? And how do we compute the performance of this platooning over the communication performance? For example, in terms of coverage of a user or load distribution or the rate distribution. So these are the main questions we wanted to ask in this work. And that what I'm going to cover today. Okay, so first we take a road and we talk about how we can model the platoon on the road. Okay, so we have two level of randomness here. We need platoons and we need vehicles on the platoon. So the platoons we can model using the Poisson point process because these platoons are formed independently, right? So the location x1, x2, x3 like this, they together form a one-dimensional PP with density lambda p. Here xi denotes the ith platoon. So here you can see this each box here is a platoon. Now inside the platoon, you have a fixed radius of A, which we call the platoon radius, right? So in that area from minus A to plus A around the center, you will have vehicles which are again is a finite point process. We model them because of some randomness can be there in the movement, so it may not be exactly possible to maintain the exact distance. So we have used the vehicles inside these platoon as the PPP itself. But this small PPP is a finite PPP with density lambda d in the area A. Okay, so in the area minus A to plus A. And the jth point of the ith platoon we call Zij, that basically is the jth vehicle in the ith platoon, right? And so this particular platoon is known as the cluster or the platoon or the daughter process, and the platoon center is known as the parent point. Okay, you can compute on the average because the density here is lambda d and the size is minus A to plus A. Overall, they will be m equal to 2a lambda d number of vehicles in each platoon. And if I take the union of all those platoons, what I get is the complete process denoting the vehicle on the road. Okay. Please feel free to ask any question if you have in between also.
Abhishek, I have a question. Can you hear me?
Yeah, sure. Please ask.
So in each platoon, you have a random number of vehicles or fixed?
Each platoon we may have random number of vehicles. So on the average, there will be lambda d into 2a number of vehicles.
So are you assuming that this is a Poisson random variable on each of them and conditioned on that number it's
yes.
uniformly distributed? It's like homogeneous Poisson process you're assuming for?
Yes. homogeneous point process in that area.
Okay. Okay. Thanks. That's all.
Yeah. Right, and there are other models available. For example, you can also think about this radius itself is not fixed. It may be Gaussian distributed or some other kind of distribution. That is also possible. And then you can also talk about like a fixed distance or some other distance. So those models are also possible. This particular model was relatively easy to work with. But again, this kind of framework can be extended to include those kind of things. Okay, so right, so this particular process, when we combine the platoons with the vehicles inside, the overall process becomes a Matern cluster point process. Okay, so so it is defined this way: the platoons, the clusters centers are PPP, and for each cluster point, its cluster is also a finite PPP. So the union of this doubly stochastic process is a Matern cluster point. Now this is on a single road. Now let's talk about how we can talk about different roads, right? So normally, if you think of a typical road network in a freeway kind of scenarios, these roads can be randomly oriented and they may be intersecting each other. So how can we model such kind of roads using again stochastic geometry? So what happens is, if you think about any particular road, the road you can characterize using the distance from the origin, which we call rho, and the angle of this perpendicular from the x-axis, which we call phi. So each line is uniquely characterized by the distance, perpendicular distance from the origin, and the angle perpendicular makes from the x-axis. So we can call them rho phi, and then you can think that each of these lines can be represented by a two-dimensional point rho phi in a different space. So we call this like L space, which is r comma 0 to 2 pi. So this is like real line, and this is 0 to 2 pi. So each of the point can be represented by a two-dimensional point in this space. So the x-axis will denote the angle, and the y-axis will denote the distance. Okay, and again, we can show that these numbers can be modeled using a Poisson point process in the L space. Okay, so there are two spaces here. The lines are actually in this real space which you're talking about, like actual deployment. But we can think of a virtual L space where each of the line can be seen as a two-dimensional point. And there, those lines, which are actually a point, can be modeled using a Poisson point process. And in the actual space, if you draw these lines, this will form something called a Poisson line process. Okay, and you can show that if there is a like the density here of lambda L, okay, then the density here will be lambda L into pi because of this addition. So once we know how we can model this, right, so that we term normally as Poisson line process. And again, if I want to formally define, PLP is a collection of randomly located and oriented lines, LIs, and each LI is actually a one-dimensional line in a two-dimensional space, and with a line density mu. Okay, how do we define this line density? You can think this way: if you take any convex body K, then with parameter Lk, then the number of lines intersecting this convex body is Poisson with parameter lambda L into Lk, where lambda L is mu L by pi. Okay, so this is how this line density is defined. Okay.
Hello, sir.
Yes.
I have a question. So, sir, are we assuming that all the platoons and all the roads are covered by single base station?
No, we have not talked about base station yet. Currently, we are just talking about how we can model the vehicular network itself. Okay, so there will be We've talked about platoons on a single road. Then I'm talking about how we can have platoons, roads, different roads. Then we will combine these two, and then we talk about how to serve these vehicles.
Okay, sir.
Okay. So if you know the parameters, I mean, just remember this, we will be using this. If you know the parameter, you can find the distribution of lines intersecting that body. Okay. Now, if I talk, let's see how we can take the platoon vehicle on a single road and how we can uh, uh, transfer that to the set of roads. Okay. So if I take this, we have taken a road in a one-dimensional space, and we have modeled the vehicles using MCP, Matern cluster trusses. Okay. This is like different platoons. Each platoon is a vehicle. So it's like a double PPP. We call it MCP. Now the road can be randomly oriented with rho and phi parameters. So we need to shift these points to these lines. Okay. So we can think of a simple transformation which depends on rho and phi. If you apply that to each vehicle here, you will basically get points on the road, right? So basically you take that one-dimensional MCP and you rotate it, substitute it, shift it to that road. Now you have a MCP on the one road. Okay, this is again a one-dimensional MCP, but this is not on a single line. This is on a inclined. Okay, so I'm just including some kind of interesting results which may be using it later on. Suppose you have this road and you want to compute how many points are there in this particular ball of radius r. Okay, so let me clarify again. There is a road going on with the distance rho angle phi. Then there is a ball of radius r from the origin. I want to ask how many points are there in this ball. Okay, so first of all, you can see this line cuts this ball to make a chord, and the chord length you can compute as 2 into r square minus rho square. Okay, because this is rho, this is r, so you can compute the chord distance as 2 r square minus rho square, and then we have the MCP, we know we can compute, it's a double PPP. So you can compute how many points are there on this lines. So here again, I've computed a PGF because from PGF, it's easy to compute the mass function and the distribution. Okay. So just like remember, you can compute the distribution of total number of points on this line. Okay. Which is given by this function, which is exponential of some g function which depends on the length of this chord. Okay, and g is given by this one, so I don't want to go into detail of this one, but this is basically just applying the Laplace functional to compute the total number of points which are inside this ball. Okay, so now once you have identified this each line, you have to do this for every road. So for every road, you have a MCP, independent MCP. You take that MCP, substitute, transform to the road. Then you take another road, take a new MCP, and again transform to different roads. And when you take a union of all those roads, what you get is basically a set of multiple roads and the platoons vehicles on each of the road. Okay, so let me show you a simple diagram. This will look something like this. You have multiple roads, and the dashed lines are roads. The blue dashed lines are roads. You have these roads, vehicles on these roads, and then there are multiple roads, and then the vehicles on all these roads. Okay, so if I compare, this is the platoon traffic. Let me again say, you have a PLP which models the roads. Then you have one-dimensional MCP on each of the road, and this as a parameter, it has a parent platoon density of lambda p. Average number of points in each platoon is m, and the platoon radius is a. These are the three parameters. Okay, and then if you take a union of all those things, what you get is many points which you can call ZIJK. ZIJK is the vehicle, kth vehicle on the jth platoon on the ith road. Okay, so there is 3 level of irregularity here. That's why we call it triply-stochastic process, and we term this PLP-MCP. If you think from non-platoon traffic, you can have the roads as the Poisson line process, but then the vehicle on the road you can just model using PPP. So this is a double layer of stochastic process, and here you have points like PIJ, which is a jth vehicle on the ith. Okay, so this people have called it different names. We basically call them PLP PPP. Right? This is a PPP derived from a Poisson line process. This is MCP derived from a Poisson line process. So the properties of this PLP MCP is you can show that this is stationary. The density overall, you can compute how many vehicles are there in a set in a unit area, and that is given by m lambda p lambda l into pi. So m is the average number of average number of vehicles in the platoon, multiplied by the platoon density, multiplied by the road density into pi. And this is actually defined as a Cox process. Cox process is nothing but a Poisson process which with density itself as random. Okay, so here you are being driven by a PLP and a PPP for this Cox process. So we have characterized the PLP MCP. I'm not going to talk about much of the derivations here, but we have computed the PGFL and the Laplace functional of these things, and they come out to be a very simple function. And you can observe that this FL is the function which transforms one-dimensional to two-dimensional. So this part is basically for each road, you have this particular PGFL, and then you have multiple roads. So they all combine together and you transform to create the overall vehicle. Okay. Now this is the vehicular part, right? You have modeled the vehicles, platoon vehicles on multiple roads. Now the second part is how do I have the communication network over it, right? So again, there's multiple ways you can think of vehicular network. You can think of the communication network where you have base station along the road, which we call roadside units. You can also have regular base station, which are distributed usually, and the vehicles are basically associated with them. In this work, we'll talk about the location of the regular base stations. So again, regular base station can be modeled using Poisson process. This is a very general model and a very popular model which has been validated that given the increasing randomness of the deployment of the cellular infrastructure, there's a PPP is a very good model which can, so if you have a Poisson process, each of the point will denote one base station, okay? And these base stations are actually coexisting with the vehicle networks, right? And they lie everywhere. And then we can assume that base station transmit with some same power. Each base station is BI, and we assume, see, this is a cellular network. So a user associates with a particular base station, right? And that base station association may depend on some criteria. For example, the user can choose the base station which has the maximum average receive power, and then it connects to that base station. Okay, so each user basically connects to the nearest base station, and once you have this kind of association, you can think that the overall area will be divided into small regions, right? Which you can think here. So every base station has some region around it, and which means all the user in this region will have this base station the closest one. All the users in this area will have the base station, closest base station, this one. So you have divided the area based on this closest distance criteria. Now you make sure that each user which lie in this basically have the best base station in terms of the average serving power. So this kind of tessellation is basically known as the Voronoi tessellation. And if you take the original point process as Poisson point process, this tessellation will be known as the Poisson Voronoi tessellation. Okay, so each of this cell basically denotes the serving region of the base station, right? And then you can compute the Voronoi cell distribution. For example, if you take the base station density is lambda b, you can talk about. Okay, let me clarify also what is a typical Voronoi cell. Right, you are seeing this particular distribution. If I pick one cell randomly, right, without any bias, so I pick any of these cells, that will be a typical base station. Okay, so basically, if I pick any typical base station, typical Voronoi cell, I can compute the distribution of its parameter and the its area. Again, the theoretical analytical values do not exist. It's a very difficult problem. So people have talked about empirical, and both of them can be modeled using generalized gamma distribution. Okay. And similarly, okay. So now let's think about this one. You have, this is a combination of vehicular network overlaid with the communication network. So as I've talked about, these dashed blue lines are the roads. These blue circles, small full circles are the vehicles. These base station are the red circles. And because of that, you have these Voronoi cells. Now you can see that each Voronoi cell has some users inside it. All the users in this cell will be served by this base station. All the users in this cell will be served by this base station. So we have that actually answers one of the questions, that you have multiple base stations which are serving multiple vehicular users on different roads and different platoons. Okay. We also assume that if any of the cell does not have a user, for example, if you look at this cell, it does not have any user, then it can stay silent, which means it will not be interfering to other base station. And that is a useful technique because of that, you can reduce the interference if the user is not in that particular cell. So you can model the active base station point process again using a approximate PPP if I know the active probability and the overall density of the base station. So now if I take any particular user, I can compute the signal to interference ratio by computing the serving power. Serving power will be given by the H0, which is the fading, and R to power minus alpha. R is the distance from between the base station and the user, regular user, and alpha is the path loss exponent. I've assumed a simple path loss based, power based path loss. So R to minus alpha is the path loss, and you multiply by fading to get the serving power. Similarly, each user will get interference from all the active base stations. So they will also have the similar term. From each base station Y, you have a fading, and you have the path loss from that base station. Okay, I've assumed the exponential distributed random variable for fading, but you can assume more complicated fadings also. Okay, and you can see that each of these on road, because of the platooning, some vehicles may be closed, and that may help in their inter-vehicular communication. Okay, so let me compare the independent movement with the platoon movement. Okay, so right. So here you can see platoons, which means there are more vehicles in each platoon, and these are independently distributed. So overall, the base station deployment is same, the road deployment is same. On each road, the deployment will be different. Okay. So what is the benefit of all this modeling? What is our goal here? As I also clarified earlier, my goal is basically to talk about the load distribution and the rate coverage, right? So again, I do not have much time, so I'm going to just talk about very simple things. What I mean by load is that if you take a typical base station, you basically compute how many users are there, right? And that is the load, right? Why is this load important? Because in two things. One is it can affect the SINR. If the load is 0, then the base station may turn off, which means the overall interference may reduce. So the 0 load probability will help us with reduce the SINR. Then you have, if you have many users, the available resources for each base station will be divided. So this will reduce the per use available resources, and that's why it will reduce the per user rate. Okay, and this is more important in SINR because if you remember the Shannon expression for the rate expression, the bandwidth comes as a pre-log factor. So if the bandwidth reduces by twice, then your coverage, sorry, your rate suddenly, immediately reduces by 2. So it's also very important to understand what is the load distribution. Okay, so I'm going to call this CM, and the way I can compute this distribution is, so if you look at this particular cell, if you want to compute the total number of users in this, you need 3 things. One is how many roads are inside this cell, basically how many roads are intersecting this cell. Then you need to know the length of each road, and which means you know the distribution of these chords. And then once you know, you basically need to know the load on each of these chords. Okay, so you need to know how many roads are there which are intersecting this cell, which are inside this cell, and on each road, what is the length of the road? Because if the length is large, you will have more number of base stations, more number of users, and then what is the distribution on each road? Okay. So again, we have the chord length distribution, which we also computed. This is one. We also computed one in this paper. Then we have talked about that. We know the distribution of Z. Condition on Z, because this Voronoi is a convex set, you can compute the total number of points, which is again Poisson, which we have showed that the number of points in intersecting any convex body is again Poisson. And then condition on number of N, you can compute the total number of points in the chord. Remember, we have computed this. If I have a fixed chord length, then we can compute how many points are there, and that is the PGF is given by this. And I can combine all these 3 together. So condition on, we have the distribution of Z. Condition on Z, we have how many number of lines intersecting. And then for each number road, we have the number of points distribution. We can combine together to compute the load. Okay, so we get this expression, and we can of course compute the moments and the PMF from this PGF. We also do a very simple calculation. See, we need this typical chord here, and the typical chord may be difficult. So we can approximate this Voronoi set with a circle, with a ball, with the same area. Okay, and we know the distribution of the area, so we can compute the distribution of this radius, and then it becomes easy because you just need to take this chord and then compute the total number of points in the chord, okay, and then average it over all roads. So this will give you a little bit simpler expression for PGF, and again you can compute PMF and this one. Okay, and then similarly, once you have this distribution, you can compute the active probability, which is the probability that there is at least one user in the typical base station. Okay. Similarly, we can compute the tagged cell. So what is the tagged cell? So as I said, typical cell is you pick one base station randomly. A tagged cell is you think about the origin and you find out if there is a user at the origin, what is the cell it connects to, what is the base station it connects to. Okay, that we call tagged base station. Okay, and there is a Feller paradox or the Little's theorem which states that these two are different, which means if you take a user and ask about the size of the Voronoi of the base station it connects to, it is generally bigger than the typical base station cell, right? Because there is a higher probability that you will select a user in a larger area. So if you take a user and ask about its cell, you will get a bigger cell, right? And this is same as when we say that if you are standing in a queue, the average length of your queue is larger than a typical queue's length. So we can compute this again. So this load on a tagged cell will be dependent on three things. One is how many vehicles are there in the platoon. So you are fixing one user, right? So once I fix one user, the user may belong to one platoon. So that load will add up. The user may belong to one line. The load of that line will add up. And then all the vehicles which are in the rest of the roads, that will also add up. So using similar techniques and approximation, you can also compute this one, right? And I cannot talk about this equation, but basically you get the load distribution on the tag cell also. And then you can compute the rate coverage, right? So what is the rate coverage? Rate coverage is basically distribution of the rate at each user. It is the probability that rate is more than some threshold. And rate is given by the log 1 plus sin r and bandwidth divided by total number of users. Okay, total number of users is m, which we have computed. This will give you rate. And I can compute a distribution of this rate. Probability that this is more than tau is given by, if you condition on the load distribution, you get probability that log 2 1 plus SIR is greater than tau upon this factor. And this will give you probability that SIR is more than this. So this is the SIR coverage, which we already know. If I put it back, you will basically get a simple expression which shows you the rate coverage of a typical user, right? Which means if you take a typical vehicle and ask what is the probability that this vehicle is covered, which achieves rate more than some threshold, this will be given by that. So let me go through the implication of my results. First is we showed that the accuracy is when we did some approximation, so we compared the exact and the approximated using this Bhattacharya coefficient, and we showed that this is very close to 1. And this, of course, reduces when we have a more number of users per platoon, right? But when we have a decent number like 10 or 15 vehicles in each platoon, this is a good approximation. Okay, so basically when the platoon has more number of vehicles, less number of vehicles, this is more like a Poisson Voronoi process. There the approximation is more better, and as the number of vehicles per platoon increases, the accuracy worsens little bit. But this is actually, we found that this is still good for all reasonable number of vehicles per platoon. Okay. We also computed some matrix. For example, we talked about the mean load of a typical base station when it is active. And we also compute the probability that the typical base station has a load less than its mean, right? So this is like a safe operational that your load is not crossing the mean, right? Which means you have enough resources. And we showed that basically, if you talk about the energy consumption, that how many base stations are off, in that case, the platoon traffic is good, which means it will have more energy efficiency. But because of the platooning, it's more chance that the base station which has one user have more users, right? So there's a platoonings which puts a correlation on the vehicles. If you see one vehicle, which means there will be more vehicles around it. So because of that, overall the load distributions becomes more disparate, which means you may have either zero vehicle or many vehicles. And because of that, your overall safe probability load distribution may get lower in the platoon traffic. Okay. Then we also showed that if you look at so basically this shows that the safe operating probability is better in the non-platoon traffic. And then I want to talk about the load balance in the tagged cell. If I look at the tagged cell, means it will always have one user because I picked one user and I'm looking at the base station which connects to that user. So let us talk about what is the probability of single user. What is the probability that the base station has only one user? And when I compare the platoon and non-platoon, I find that there is a higher probability of having only one user in the non-platoon traffic. While the platoon traffic, there is a less probability of having one user, which means if the base station is active, it has less probability it will have one user, and this will improve the overall efficiency because the base station is not wasting its power to just serve one single user. Okay, we have also computed the average load and compared that. We found the average load on the Platoon traffic is more, and then we also compared the safe operating probability again, and which also showed that it is better in the non-Platoon traffic. Right. Now let us come to this result. When we saw that there are two things. The Platoon traffic has a lower on probability. It is a higher off probability, right? But it also has a higher per base station load. So these are contradictory things, which means you do have a less activity, which means you can save power, you can reduce interference, but you also have on an average high base station load. So if the system bandwidth is enough to support this high load, then you are better in the PTS because your SINR will decrease. And that is the reason we actually wanted to see how the rate coverage behaves. Okay, and we saw that the rate coverage is basically, if I compare that together for one base station density, they comes out to be close, right? Actually, I do not have a result here. I'll just show you a little bit later after this talk. And we also, what we did is we plotted the rate coverage with the active base station density. And we showed that if we have a fixed base station density, then, if you take the same active base station density and compare Platoon and non-Platoon, the Platoon traffic will give you better rate coverage. Okay, so I'm just going to show you just after finishing this one. So let me talk about the main takeaways here. In this work, we developed a comprehensive approach to modeling and analysis of Platoon vehicular traffic. This modeling gives us a new novel point process which captures the three layers of randomness. One is the roads, orientation and layout, then the Platoon's placement and the user's placement. And then we characterized this point process. We talked about different load distribution, and we showed that the Platoon traffic scenario can work better if the system bandwidth is enough to support the load, right? And there is one more point that because of this platooning, you can actually just enable the Platoon center, right? And ask the Platoon center to talk to the base station. And in that case, your load actually decreases because now you only have to support your Platoon centers. And if we implement that, of course, in that case, the Platoon traffic will give you even better coverage from that. Okay, so this was basically what I wanted to cover. Let me just show you this result quickly. I think somehow the presentation did not have that result. Right, so this is a result I showed you, that if you see the base station density and plot the rate coverage, you see Platoon and non-Platoon are almost same. But if you plot them with respect to the active coverage probability, active base station density, we can see the Platoon traffic at the same active base station density is giving very high rate, which means you require less number of base stations to achieve the same rate coverage. Okay, and again, when we talk about this, is with the fact that when we have this vehicle to infrastructure communication only with the Platoon, this will give you even better performance. So that's all from my side. I'm happy to take any questions if there are.
Yeah, so Abhishek, I have a few questions actually.
Yes, sure.
Can you hear me?
Yeah, I can hear you.
So first thing is that see, the platooning has some other advantages also, which I mean, maybe I felt that was not touched upon. For example, I mean, what platooning saves you in some sense that you can have better V2V communication, right? If you didn't have platooning, you probably would have to do more V2I communication, right? And I mean, and it's, but these things you didn't measure somehow. So I was a bit surprised. I mean, like, how did you decide that this is the metric which people would care about? That's what I'm wondering.
No, but you're correct on this. Actually, that is a very important parameter, and we are working on that, right? So this itself, load distribution was very large work. So, but planning and the future thing. So the student is already, and we are already working on this one. We are our interest would be, as you said, the main point of platooning is, I mean, there are 2 points. One is you can increase the load capacity. So basically, you have to think also how you can incorporate somehow this load capacity along with the communication performance. Right?
Yes, I was going exactly. I was going to say that next. Actually, platooning helps you have more cars on the road, right? I mean, that's also something. Yeah.
So we have to think. We have to think how we can incorporate that. That part is still remaining. We are still figuring out how we can combine these two. But the other part that definitely Platoon helps in the communication with the vehicle, right? The main thing is you have some guarantee of the distance, right? So yes, we are working on how we can incorporate this V2I along with the V2V communication. And then together, as we think of, right? So we are already working on this. We will have a result very soon. And that is where we would like to do more. I mean, we would like this platooning will become more clear that why this is the way to go. When you can see that because of this vehicle-to-vehicle communication, you will have less load on the base station. So that performance will increase, and also vehicle-to-vehicle communication will increase. So overall, the connectivity of vehicles will improve.
Thanks, Abhishek. Also, I was thinking, I mean, sorry, I mean, okay, let me get my thoughts together. Maybe others have some question. I'll come back.
Yeah, sure. Please ask if you have any question.
I had a question related to the independent movement of and the modeling of with point Poisson process. Usually, when on road, you see that the slower vehicle causes a bunching of vehicles behind it. So, how does or what is the correct way to model that into your assumptions?
So basically what we thought of here is more like a expressway communication when you have expressway and the vehicles are moving on that. So in that case, it is generally ensured that you do not have such kind of buildups because there is no signals on the expressway. So where this model will be good. Now, if you want to talk about like city traffic, right? There, the vehicles are generally again depends on Indian city or a US city. In a typical Indian city, you have vehicles basically just together, right? And in that case, the modeling would be a little bit difficult because you may have to use. I mean, it's more like look at deterministic deployment where vehicles are just like one after each other. So that's a difficult thing to model actually. Right. One way can be you can have something called a Matern hardcore process, where you have multiple points which are have some distance between them, right? Or you can have some kind of new process where you can assume some fixed distances between the vehicles, right? So that is in fact possible, and the analysis would be similar to that. And then I would like to tell you one important result in stochastic geometry. People have showed that the exact point process sometimes does not matter because overall trends would be similar. This is very common in the when we talk about base station deployment. When you have other type of deployments, there is some fixed gap in the performance, but overall the trends you get is similar to this thing. And what helps here is basically fading and shadowing. Once you are fading and shadowing, the geometry is modified using these random variables. So all the distance which were actually deterministic becomes more random there. Right. So that's why there is a tractability and accurateness trade-off. If you want a very accurate model, you may lose some tractability, which is provided by the Poisson models. That is the main reason people go for these Poisson models. But as I said, it is in fact possible to think of more point processes which can correctly model Indian cities or US cities or dense urban cities where you have more buildup of these kind of vehicles.
Thank you.
Yeah, thanks, Abhishek. Actually, I had a question along the same line, but I think you already sort of answered that. So I was wondering that for independently moving cars, this PPP makes sense, right? Poisson point process. But when you have platooning, the cars in the platoon would have a little bit more deterministic movement, right? You would expect them to have some coordinates. So there, assuming it to be PPP was maybe it's a more like your, as you said, modeling choice. And I was wondering if you have empirically verified the robustness of your assumption. That means even if your simulation does not follow PPP, but you see that the results are actually similar.
Yeah, we did some simulation on that. Right? Probably we did not talk about extensive ones, but we did some simulations. We are again trying to compile some other things also. And then we are trying to compare different, I think Kaushlen had some ideas about how you can compare different city scenarios and then see where this model will be better or not. But again, see, if you look at these platoons, overall the platoon centers are still PPP, right? That is a justifiable assumption. Now the second thing is vehicles inside the platoon, right? Now this A radius is generally small. So even if you take like, fixed distance or random distance, overall communication performance is not going to change much, right? Because even if you put them deterministically, this change of 1 meter, 2 meter is not going to change.
No, I agree with you. Yeah, that's fine. Yes, I agree. Yeah.
So that is the whole point of, we can take deterministic one, but if you have worked with stochastic geometry, you may have some idea, but stochastic geometry very soon becomes very difficult. Like if you just have one realistic assumption, you change fading from exponential to Nagami and things become very different. So that is
no, I agree. I think if you don't have right assumption, the math will not work out. But I was thinking, but in simulation, you can verify and check that we can do whatever, right? And see, right? And we can say that okay, even if my assumptions are not this, still it's not so awful.
Yeah, simulation we did some verification, right. And that we do not include in the paper. But yes, we did some verification on that, and we are also thinking of comparing, thinking of different scenarios where this will work. In this paper, we mainly focused on expressways, where things looks like more reasonable.
Thanks, Abhishek.
Are there any other questions? If there are no more questions, let's end the talk. So thank you, Dr. Gupta, for an informative talk. As discussed before, we would like to remind the audience to subscribe to our Google Groups, which is the mailing list for information on future talks. You can also visit our website for more details. The links have already been pasted in the chat box. The link to the recorded video will also be posted on the webpage. Thank you and have a great evening.